question we left from last time. Okay, yeah. So when we solve this non-homogeneous linear system of ODE, there is one small technical problem. Remember here? Yeah. Because when we choose this parameter A, there is a small technical problem. So what is the right way? Yeah, because here we need to consider a general coefficient matrix. Yeah, because this case, very simple. Yeah, so here we want to consider the general case. General case. Yeah. So we need to find a general method. Yeah. For the special case, by observation, but if I change the coefficient numbers, is there some systematic way to find the answer? Yeah. So I want to answer this question. Some systematic way to find the answer. Yeah, all right. Yeah. Here, let me give you the answer. Yeah. Because in the coming homework assignment, probably I try to make a question to let you do it by yourself. Yeah. Yeah. So here I'll tell you the method. Yeah. All right. To understand this method, yeah, so you need to have some knowledge. Yeah. So here, let me give you some overview. Yeah. The knowledge we need from linear algebra to answer this question. So what's that? The first concept, the inner product. You need to know the inner product concept. Yeah, very easy. Yeah, but here I just, explain a inner product concept. Yeah. Two vectors, UV or AB. Yeah. So yeah, here let me use UV vector. U vector and V vector. Okay? So we do inner product between two vectors. Right? Yeah. The definition of that, yeah. Here, let me just use the simplest case, two-dimensional case. Yeah. Although we can generalize to n-dimensional, yeah. But here, it's good enough to consider two-dimensional. U1 V1 plus U2 V2. That's the inner product between two vectors. Okay, so U vector, it's U1, U2 components. V vector, V1, V2 components. Okay, all right. Yeah. So for inner product, when we do this operation, there is a geometric meaning. Yeah. So here we need to use the geometric meaning of inner product. What's the geometric meaning? Geometric meaning. Yeah, important geometry. Inner product closely related to the angle between two vectors. U vector, we draw U vector, and then we draw V vector. Then suppose the angle between these two vectors is theta. So this inner product can tell us how large is the vector between two, the angle, how large is the angle between two vectors. Okay? Yeah. So we can find a formula to get this vector. All right. Now, there is a special case about this vector. When theta equals 90 degrees, right angle, 90 degree. Yeah. Then these two vectors are perpendicular. Yeah. Like this. The angle is a right angle. The two vectors are perpendicular. Relationship between these two vectors. So the perpendicular condition is its inner product equals 0. Okay? U dot V equals 0. Okay? Yeah. That's the geometric meaning between two vectors. Okay? All right? So with this understanding, now we use this property to solve this small technical problem. We consider between two vectors, we want to use for a current vector, we want to find another vector that is perpendicular to the current vector. Perpendicular, all right? Yeah, because 0 is gone. We want to use this property, annihilate. So the perpendicular vector annihilates the current vector, make it 0. Using this property, let's find the unknown parameter A. All right, let me show you. So this is the idea. Okay, this is the idea. All right. Yeah. So now we consider the general coefficient. Yeah. So not that special. All right. All right. Now, A matrix, the general A matrix. Let's assume there are two vectors. Okay. All right. A1 vector, how about it? And A2 vector, both column vector, okay? Yeah, both column vectors. All right. Now, there is a condition. Remember? Yeah, because our A matrix here, we know there is one special condition. The determinant of A equals 0. This condition is needed. Okay? Yeah. This condition is important, right? Yeah. So we need to use this condition. Yeah. Why? Yeah. Let me explain why. Okay? Yeah. Why this condition is important? Yeah. Because if determinant of A is not equal to 0, then A is invertible. A inverse exists. Okay? Yeah. Then we multiply A inverse both sides, right? So if we multiply A inverse both sides, then V1, V2 here equals A inverse times that A plus 6, A minus 2. Then for any A, we can find V1, V2. Okay? Yeah. So that's not our situation. Our situation, because remember, this A matrix come from eigenvalue. Yeah. So original A, yeah, this A matrix is not original. Original A matrix minus lambda I, right? That A comes from the original A matrix. Here I use A0 minus lambda of eigenvalue times I matrix. So the determinant of this matrix must be 0. So that's why we need this condition. All right. Yeah. So how to use this condition? Now. All right. Here, I need to use a special concept. Yeah. All right. Linear span. Yeah. Have you heard of a concept called the linear span concept? We need to use this linear span concept. Yeah, what's that? Linear span concept, we use notation. Yeah, so people use this notation. Yeah. Arrow bracket A1 and A2. Yeah. Represent. We generate a linear space spanned by these two vectors. Linear space spanned by these two vectors. That's called a linear span. All right? Yeah. So how to generate? Use linear combination to generate. That's simple. All right? So how to generate this linear span? C1, A1 plus C2, A2. Yeah. Yeah. So then it's a linear space. So we get a linear space. All right? So that concept. All right. This linear span space is a subspace of the current Euclidean space. Yeah. So, yeah, because two-dimensional, our current space, what is the whole space? Whole space is R2 space, right? R2 space. Yeah. Yeah. Because R2 space formed by, A, B, two components, little a from R1, little b also from R1. Okay? So that put them together, so that's R2 space. The whole two-dimensional Euclidean space. That's the R2 space. Yeah, it's a little abstract. For some students, yeah, probably a little abstract. Yeah. Yeah. But we need this kind of understanding to understand the linear algebra. Now, that's the foundation part of linear algebra. All right. Yeah. Then this linear space is a subspace of the whole space. It's a subspace. Subspace of the R2. R2 is the whole space. Yeah. So that is a smaller, it's a subspace. Yeah. All right. Then, now, because it's a subspace, it's not a whole space, then we can find a vector that is perpendicular to this linear span, subspace. That means, so if a vector perpendicular to this subspace, all the vectors inside this subspace, if we do inner product with that special vector, yeah, yeah. So we can call the normal vector, okay? That vector, normal vector, yeah, perpendicular to everything in the subspace. You do linear product, you get 0. Okay? All right. Now, you find one vector that is perpendicular. Yeah. So one vector. Let me call it. Find D vector. So you need to find a D vector such that D vector is perpendicular to A1 vector, and the D vector also perpendicular to A2 vector. Okay. Can you find it? Yeah. So we need to do this step. Find one D vector perpendicular to these two vectors. Yeah, actually, these two vectors, linearly dependent. Yeah. So if it's perpendicular to the first one, then it must be perpendicular to the second one, right? Yeah. So that's easy. You just solve A. Yeah. So A matrix, yeah, A11, A12, A21, A22. You solve X1, X2, equals 0. Okay? Yeah. Now let me erase this a little bit. Yeah. Okay? Yeah. All right. You solve. Sorry. Yeah. 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 All right. Transpose. Yeah. All right. So here to solve. Yeah. Because the direction. Yeah. Because when we consider column vector, right? This time you should put a x1, x2 as a row vector. Solve this equation. How about that? Okay? Put it at the left-hand side. x1, x2, you use it as a row vector. So you do multiplication from the left side. Yeah. Because when you do multiplication, the row vector, the column vector, you do inner product, right? You do inner product. 0, then this vector and that vector, inner product equals 0. Okay? Yeah? Yeah. If you feel doing left-hand side multiplication not very natural, you do transpose. You get a right-hand side. Okay? So you do transpose. Yeah. Yeah, here there's the space. Yeah, I need more space here. Transpose. When you do transpose operation, you get the right-hand side version. Okay? A11, A12, A21, A22, then x1, x2 equals 0. Okay? Yeah. You do transpose of. You can use a form that you are familiar with to find x1, x2. Yeah. Yeah. But either way, you just need to find x1, x2. When you do matrix multiplication, you get a 0. All right. This x1, x2, you use it as this d vector. All right. D vector. You have this d vector. All right. Now, after you get a d vector, you are ready to find this little a. How about that? You use d vector to do inner product with, d vector, yeah, because here, it's better we use the, transpose of d. You do, matrix product. D vector, you do matrix product, D transpose, with the right-hand side. Left-hand side, yeah, you get a 0, right? Right-hand side, this D vector multiply this A plus 6, A minus, this vector must be 0. Can you find A? Right? Because D vector is known. You have this explicit numbers for the D vector, right? You have the explicit numbers for D vector. Okay? So then you do matrix multiplication. Yeah, you get an equation with a parameter, so you can find it. Okay? Yeah. If you still feel intrigued, I can show you a concrete example. So here I describe the general method. Yeah. So if you need my concrete example to going through everything like this, yeah, I can make one. Okay? Yeah. Make one step by step going through. Yeah. Inner product. D. How to find this D vector. Yeah? So this is a systematic method. Yeah. You do not need to use the eye observation, because when a number is very complicated, nobody can use eyes to find a solution. No. So we need some method that does not rely on our observations. Yeah. Here, that's the one. Okay? All right? Yeah. So I may feel that you may need one example. Yeah. So I need to make one. Yeah. Yeah. After I find a good example next time I show you. Then you can do it in your homework assignment number 3. So you should also, because we also have a coming quiz number 4. In this quiz number 4, I need to give you several questions related to linear algebra knowledge. For example, as I said, the geometric meaning of inner product of 2 vectors. I give you 2 vectors. Then I ask you to find the angles between these 2 vectors. You can find a formula. So from Webb, some formula, angle. Okay, So how to calculate the angle? Very easy. Here we only use the 90-degree angle. Okay, 90 degree, 0. If it's not 0, then not 90 degree. Then you need to, apply the formula. Find what's the angle. All right. Next, now we start the introduction part. Here. Periodic function. First, let's look at the simple concept, periodic function. All right. So why periodic function? Later. So we can see. So when we start, we want to consider relatively simple function. So this periodic function. Relatively simple. First, some real world phenomenon has this property, periodic property. A few. Rotating parts of machines. Periodic. Another, alternating electric circuits. So that's another important phenomenon. Or the motion of planets. So you see. But later you will see, although there are many important real world phenomena, they are periodic. But if we can only model the periodic phenomenon, that's very limited, right? Because a lot of other things not periodic. How can you model non-periodic phenomena, right? So later we need to, after we study the periodic phenomenon, then we need to extend it to cover non-periodic phenomena. All right. How to represent so many different types of periodic function. Here, let's focus on the periodic function. What is the best way to model the periodic phenomena? So you want to use periodic functions to model periodic phenomena, right? So it's not natural. If you use non-periodic functions, then because the structure not compatible, so your calculation, you may have a lot of errors in your calculation. So here, let me give you a simple example. Non-periodic functions. So people frequently use to model the data, real-world data, polynomials, right? Or monomials, let's say. Monomials, the first the simplest monomial, then x squared, x cubed. Yeah. So that's one of the commonly used simple basis functions people use to model data. Yeah. It's non-periodic, right? Yeah, it's non-periodic. Yeah. So here you can see, if we use these basis functions to represent periodic objects, so you can see, so a lot of unnatural things could happen. Yeah. Convergence is one, right? Yeah. How to get your series convergent is one. Another, stability, stable, well, fluctuation, okay, error, that kind of thing. Yeah. A lot of things because the structure not compatible. Okay, yeah. So we want to use suitable representation functions, yeah, natural periodic functions to model periodic objects. Yeah. All right. Yeah. Simple, flexible sine, cosine, the best candidates. Sine function, cosine function, periodic, simple, nice shape, to model the periodic objects. Yeah. All right. Definition. So what's the definition of periodic function? Yeah. A function f of x is called periodic function if f of x is defined for all real x except possibly at some points, some points, breaking points, special breaking points, and if there is some positive number p called a period of f of x such that f of x plus p equals, so you add this period number, shift, you get the same value. So when you shift 1 point by certain unit, p units, okay, so the function value does not change. And this property holds for all x, not just for one x, okay? Or not just for some of the x, for all x in the real axis. Yeah. That's the definition of the periodic function. Okay, yeah. All right. Observation, because based on this definition, you can see if f of x plus p equals f of x, then we can conclude f plus n multiple, n some integer, positive integer, negative integer, n is an integer, x plus np also equal to f of x. Then, because we want to define a concept, period concept. What's the period of this periodic function? So to define period, NP, we don't want to call NP period, right? 100p, 57p, we don't want to call n multiple of p as a period. So we need a concept called a fundamental period. The smallest possible period. The smallest positive period. It should be a positive number, not negative. Smallest positive period. We use that as the fundamental period. Then, in our discussion, so we like to use the fundamental period when we start our discussion. Then later we can, when we need, use the multiple of p. We can use it. All right. So here, another thing, yeah, so I want to explain a little bit. Except possibly at some points. Do you feel strange a little bit? So why except possibly at some points? Yeah. So yeah. There is some special meaning behind it. Yeah. So why people put this kind of vague information there? Right? Yeah? Yeah. Vague information. Yeah. People do not describe it clearly. Yeah. Put things like that. All right. Yeah. So let me explain the reason. Periodic function. All right. Suppose you have a periodic function. All right. Then you find sine cosine representation of a periodic function in a perfect way. All right? Yeah. Okay. All right. Then sometimes in the real world situation, the whole representation is true everywhere except at some certain scattered points. Not true. Okay? Yeah. Yeah. So in that case, we allow it. Okay? Yeah. So our representation. So we accept it in our representation. Yeah. Because later you will see, we will have the cases for that. It appears at the discontinuity points. Now, if the function, there are some discontinuity points in a function. So at that place, when you do the modeling, then in those points, your formula will be different, slightly different. Yeah. All right. Next, trigonometric series. Sine cosine. Now we need to study sine cosine representations. Yeah. All right. The definition of trigonometric series. Yeah. This is the definition. Okay. Yeah. All right. Yeah. Now we want to study the trigonometric series. Yeah. All right. All the trigonometric series are based on a system. Yeah, yeah, because we use coefficients. Then we multiply sine cosine functions of nx. Yeah, multiple n positive integer multiple of x. Yeah. So these functions, yeah, so we'll put them together. Yeah. So we get a set of functions. Yeah. This set of functions has special properties. First, they are linearly independent. All these functions are linearly independent. Yeah. So you can calculate the Wronskian, yeah, if you want. Yeah. Linearly independent. Yeah. Any of them. So you select, right? You take out. You calculate the Wronskian. It's non-zero. Linearly independent. That's the first. All right. Then there is another nice property. Another nice property, very important, we need to use. Yeah. It's called orthogonality. Orthogonality. That's very, very important property. Yeah. So what's the orthogonality? All right. Convergence of a trigonometric series. Another important question. Convergence. Yeah. Yeah. Later we will look at it. Yeah. All right. The trigonometric system is orthogonal. Yeah, so this property. Yeah. We need to use this property to calculate the Fourier series. Orthogonal. Yeah. So what's that? All right. For m not equal to n, m not equal to n, yeah. Yeah. All right. Then we take integral in the period, 2 pi period, from 0 to 2 pi. Yeah. Cosine of nx times sine of mx, mn different. Yeah. Integral is 0. Yeah. For any m and n, different. If the same, non-zero. Okay? Yeah. So, oh yeah, oh, so here even same is also 0. Yeah, because the function different. Cosine function, sine function different. So even m and n the same, the integral is still 0. Yeah. All right. But for the same function, then when m not equal to n, the integral is 0. Yeah. But m and n same, non-zero. Yeah. Yeah. So same function, m and n different. So the integral must be 0. Okay? Yeah. All right. Yeah. So these functions are linearly independent. All right. Yeah. Orthogonal. So these 3 0 integrals can tell us these functions are orthogonal. Okay? All right. Yeah. All right. Question, can we represent any 2 pi periodic function in a trigonometric series? That's our next question. We need to study. Yeah, this is okay. All right. Before we go to the next slide to answer this question, yeah, I want to explain a little more about these two concepts. One is the orthogonality concept. Another is the linearly independent concept. Yeah. Are they correlated? Yeah. Are they correlated? Yeah. All right. Yeah. So orthogonal. Yeah. Let me explain a little more about this orthogonality property. Yeah. All right. Orthogonality, yeah. If we use the geometric understanding, that's the perpendicular. Okay? Yeah, same thing. 2 vectors are perpendicular. We can also call these 2 vectors are orthogonal. Okay? All right. So here, yeah, vector, 2 vectors. Yeah. So orthogonal meaning yeah, in geometry, yeah, you know, yeah, same as that, perpendicular. Perpendicular, okay? Yeah, orthogonal, yeah, this kind of, notation, yeah. That means when you do inner product between 2 vectors, you get 0. Inner product between 2 vectors, okay? Yeah. So the inner product of these 2 vectors, if they are orthogonal or if they are perpendicular, okay? You have these 2 vectors. Inner product of these 2 vectors is 0. Okay? Yeah. All right. Then, what is a vector? Yeah. Let's understand what's the meaning of a vector. Okay? Yeah. Vector. Can we generalize our understanding of vector? Vector is an object. Vector is an object. Okay? Yeah. Yeah. All right. Object. Here, so my question is, can we treat each of these functions as a vector? It's an object. Its form is different from, but it's some mathematical object. Object. Okay? All right. Now, we generalize the inner product between two vectors to inner product between two functions. Can we define inner product between two functions? Yeah. The definition of two functions, the inner product. Okay? Yeah. So what's the inner product? Inner product of two functions. Although, yeah, so we know functions different from vector, but now we treat them, they're objects. So we want to have the inner product defined, yeah, so some integral, yeah. Here we use from 0 to 2 pi. Yeah. So, actually, 0 to 2 pi special numbers, we can use the general AB number. Okay? AB. F function and the G function, this we call the inner product of these two functions. Okay? Yeah. Inner product needs to satisfy several. Yeah, inner product should have some properties. Yeah. So this definition, yeah, we can check. It follows all the properties it is required by inner product concept. Yeah. All right. Now you can see, yeah, based on this definition, then these two functions are orthogonal. Why they are orthogonal? Because their inner product equals 0. So that's why we call orthogonal. Inner product is 0. Yeah. Inner product gives the angle between two vectors. Here, the angle between these two vectors equals 90 degrees. Yeah. Orthogonal. Yeah. So you can understand in this way. All right? Yeah. Yeah. All right. All right. So so with this understanding, yeah. So now we treat these integrals as inner product. All right. With this understanding, now can we use the orthogonality property to derive this linearly independent property? Because all these functions are orthogonal. All these functions are orthogonal. Does it imply all these functions are linearly independent? So that's my question. Okay? Yeah. So here, all right. So let me write it clearly. More specific. More specific. Yeah. All right. Assume, yeah, F1, F2, dot, Fn. So here I tell you these n functions are orthogonal. These functions are orthogonal. Now, can we see that these functions, yeah, we derive? Yeah, can we say they are linearly independent. Because here we don't want to calculate Wronskian, right? Too complicated. Because these functions, too complicated. We don't want to calculate the Wronskian. Right? Yeah. All right. The answer is yes, we can do it. We can do it. They must be linearly independent. We can use the definition. We can use the contrapositive method. Apply the definition of linear independence. Let's assume they are linearly dependent, and we get contradiction. We apply the orthogonal property of these functions. We can get a contradiction. Then your assumption is wrong, so they must be linearly independent. Yeah. So we assume if they're linearly dependent, then we do inner product. Okay? Right? So we get 0. Yeah. All right. Yeah. So So I have a few minutes. So actually I can do it quickly. Yeah. All right. Now, if they are linearly dependent, can we find K1 F1 plus K2 F2 plus all right, so here, yeah, let's do this way, yeah. Kn Fn, so we do not need to use contrapositive. Yeah, let's say if there exists K1, K2, Kn, all these constant, we calculate this linear combination equals 0, then we can show all these k's must be 0. All these k coefficients must be 0. Then we can make conclusion, right? Yeah. So you cannot find non-zero. So you can now find a set of n coefficients, k1, k2, k3. They are not all 0. They are not all 0, such that you do linear combination of these n functions, you get 0. You cannot do that. All right. So here, let's do this. Now, I do inner product of f1 with this function. How about that? Yeah. Equals 0. I do inner product. Okay? Inner product, when I do it, yeah, because the inner product, it has the linearity property. Linearity. So can we take out K1, F1, F1 plus K2, F1, F2 plus Kn, F1, Fn equals 0, right? Yeah. Then, by the linearity property of inner product, so we can factor, split, inner product. But we know they are orthogonal, right? Yeah. It is known these functions are orthogonal. What does it mean? The inner product between two different functions must be 0, right? F1, F2. 0, all the terms, the inner product between two different f functions must be 0. So all the terms, but only the first one non-zero. Okay? Yeah. This is non-zero. Inner product between the same function, non-zero. Yeah. Non-zero K1 times a non-zero number equals 0, so that means K1 must be 0, right? K1 times a non-zero number must be 0. So K1 must be 0. K1 must be, can we use F2 to do inner product with the linear combination of the functions, also 0? If we apply K2 to inner product, we get a K2 0, right? Then we do K3, K4, all of those functions, then we get all the K functions must be 0. Does it mean linearly independent? This function must be linearly independent. Because any linear combination of these n functions, if it is 0, then the orthogonality forces it. All the K coefficients must be 0. That's the linear independence, right? Yeah. So we prove it. Okay? Then, if we have this, then the immediate consequence of this property, nice property, no, it's a nice property, immediate consequence, we do not need to use Wronskian to check linearly independence, right? Yeah, we don't need to use Wronskian. We can use inner product to help us check linearly independent or not. Is it better than Wronskian? It's better than Wronskian, right? Yeah. Because Wronskian, you need to calculate first derivative, second derivative. Yeah, Wronskian, yeah, may not be f functions. Wronskian, f functions. First derivative, second derivative, the derivatives. How do you know these functions are differentiable? This function may not be differentiable, right? Yeah. The functions. If they are only continuous functions, no derivatives. Or, although they have, some of them have the first derivative, they do not have second derivatives. They do not have third derivatives. How do you calculate Wronskian? But this way, inner product, no derivative, because we calculate integral, right? We calculate integral, continuous function, we can always calculate integral. So much better than the Wronskian, right? Wronskian has limitation, has big limitation, because it's not differentiable. Your functions are not differentiable. No. So this way, much better than Wronskian method. When you check linearly dependent or linearly independent, much, much better. More robust, right? Yeah. So that when the Wronskian fails, Wronskian method fails, this also works. So more robust, this method. How about it? Yeah. Okay. All right. It's a break time. Let's take 10-something minute break. Then we continue.